Hello. We'll be doing some chemistry today, starting the first chapter, atomic structure. We're going to organize this into 4 different parts, starting with the particles in the atom and atomic radius. Firstly, we have the atom, which is the smallest part of an element that can take part in any chemical change. It's the smallest thing we can ever achieve, really. They're made of protons, neutrons, and electrons. Electrons are found in the outer shells that are mostly empty space, and these electrons sort of spin around the atom a lot, and the electrons move around really quickly to try to avoid the other electrons as well. We call this electron spin pair repulsion, where the electrons don't try to touch each other. Atoms are generally really small. They have a lot of empty space between the shells and the nucleus. However, the nucleus is very dense and it contains a lot of protons and neutrons in that middle. Then we have the masses and charges. I really recommend memorizing this table if you haven't already. We have the symbols, which for electron you can write as E or an E to the power of like a negative, not -1 necessarily, but just E minus almost. Neutron, proton, or N and P, sort of simple to memorize, just the first letter. The relative mass, neutron and proton are both relatively 1. However, electron is pretty much 1 over 1,836. Pretty much we summarize it as 0 when we do a lot of our calculations. We say it's negligible. And the charge, electrons are negative, neutrons are neutral, and protons are positive. So knowing this, we can infer that all the mass of the atom is in the nucleus, because a neutron and protons are what compose the nucleus, and all that positive energy from an atom is from the nucleus, while all the negative energy is from the shells. So sometimes AICE will give you this sort of picture where they have a negatively charged plate at the top and a positively charged plate at the bottom. And they'll send a proton, a neutron, and an electron quickly through these. They all start at the same velocity. And we'll notice that the electron is very quickly deflected. It very quickly goes away from the negative at top and goes towards the positive side. This is because it has a smaller mass. So imagine you trying to throw a paper ball versus trying to throw a bowling ball. The bowling ball is just sort of going to not go as far as you want it to. It's not going to go quickly. And versus the proton, which it takes a while, but slowly goes up towards the negative. It's attracted towards the negative. Opposites attract in this kind of case. And the neutrons are not deflected at all because they have a neutral charge. So they don't care about protons. They don't care about electrons. They're just going their own way. And we have 3 things we can calculate with atoms. We have atomic number, nuclear number, and the charge of an atom. So atomic number is just the same thing as the number of protons. Tomato, tomato, it's the exact same thing. You can always look at the periodic table for this number, unless they don't give you what the element is. Then there's a nuclear number, which is also known as the mass, which is the number of protons plus the number of neutrons. And if you want to solve for neutrons, you would just subtract the protons on both sides, so you have nucleons minus protons. The charge would be protons plus electrons, where electrons are a negative number, or you do protons minus electrons, where electrons is a positive number. Either way is going to work. Just remember that your protons are positive, your electrons are negative, and you need to consider that in general. And so the electron number is going to be the charge minus the proton number in case you need to work back in any kind of way. Alright, this is so extremely important. There are 4 things to describe trends in this chapter. This is how you get marks for this section. The 4 things are nuclear charge, distance from the nucleus, shielding, and spin pair repulsion. Nuclear charge is the atomic number. The higher the nuclear charge, the more attraction of electrons, because if you have a really positive central base, the electrons that are negative are going to be like, ooh, positive, we want to get closer to that, right? Then there's distance from nucleus. Electrons that are further away are going to be attracted to the nucleus less, because they're so far away, maybe they can't. Almost imagine that if you're trying to go see a concert, if you're in the front seat, you're going to be very engaged with what the concert is. But if you're in the way back, yeah, you're still watching and you're still sort of attracted to it, but you could leave to go to the bathroom and not really miss too much if you're in the way back. Then there is shielding. Shielding is when the inner electrons are sort of blocking the outer electrons from getting attracted. It's almost like that concert metaphor once again, where those people in the front are sort of preventing you from getting very involved in that concert. Then we have our last and final one, which I mentioned earlier, spin pair repulsion. It's when electrons in the same subshell are repelled from one another. This is going to make it easier to remove electrons and that kind of stuff. This is almost sort of like when you're hanging out with someone you don't really like, and let's say you have to study for something. In in general, you might not want to study for whatever exam you're trying to prepare for, but if you're around someone that's really annoying, you might go, actually, I'm gonna go study, I'm gonna go do that. So it's easier to remove yourself. It's easier to go to things that you may not have previously gone to do that. Spin pair repulsion. That's sort of what electrons are going through. They don't want to be there, and so it's really easy to remove them. So there's two cases where we use these four terms. One is when you're talking about the radius of an atom, and the other is ionization energy. Both are in this presentation. The first is atomic radius size. So atomic radius size is just the radius of an atom, the size of an atom. We'll start with going down the group. So going down the group, we see that these atomic radiuses are getting bigger. And if you think about it, it makes sense. Because down the bottom left, we have a picture of hydrogen, and we have a picture of cesium. Which one looks bigger? You're going to say cesium because it has more electron shells, and that's essentially the idea of it, that there's more shielding involved, you could say. So these outer electrons are not getting heavily attracted towards the nucleus, therefore allowing the atom to be bigger overall. And also, protons attract electrons. We generally know that fact. And to the right of the periodic table, we have more protons than we have on the left. For example, if we look at lithium versus fluorine, lithium has 3 protons, while fluorine has 9 protons. So those 9 protons are going to work a lot harder to get those electrons to come close to it, therefore making the atom smaller overall. So pretty much a summary of all of this is that the biggest atoms are in the bottom right. But now we have ionic radius size. So ionic radius size is when an atom goes through an ionic bonding and becomes an ion. An ion is an atom that has lost or gained at least 1 electron. This can be 3 electrons, 2 electrons. It really depends on where it is on the periodic table. For example, group 1 will gain 1 electron. No, will lose 1 electron. Group 2 will lose 2. Group 3 will, or 13 will lose 3. 14, this can vary. It can gain more, it can lose more. It really depends. Then and so on and so forth, except we get till group 15. Group 15 is where it's going to start gaining electrons. That is because electrons generally, not electrons, but atoms generally have this octet rule where they want to have 0 or they want to have 8 in their final shell almost. So ones that are on the left of 14 are going to lose electrons, and the ones on the right of 14 are going to gain electrons. Because if you think about this, it's almost like a pizza. And let's say you're getting a pizza delivered to you, right? You want all 8 slices to be there. You don't want to open up your pizza and see just 7 slices in there. You're going to look at the delivery guy and be like, what did you do? And it's almost be better to receive an empty box rather than just 1 slice. 1 slice sort of is like teasing you into pizza. So that might be a weird metaphor for it, but you want 0 or you want 8 generally with. That's how atoms generally work when they bond. There are some exceptions to this, but we'll go on to that in a later chapter. We can first start with how going down a group, we have the same reason as we had last time. There's more electron shells going down, and that's going to lead to a bigger size, and that adds to more shielding. So they're being less attracted to that inner nucleus. And if they're less attracted, that means they're generally expanded more, so they're going to be bigger overall. So when we generally talk about how an ionic radius is going to change across a period, it's really weird to describe, and you can already see how I have 2 arrows going in separate directions. So we'll start with on the right side. So if an element gains an electron, its ionic radius is going to be bigger. It's getting something extra, so it's going to be bigger. For example, we have fluorine, which has 7 electrons in its outer shell. It's going to get 1 more, and that's going to make it bigger overall. And noble gases are the biggest on the way right. And however, on the left side, we have hydrogen, lithium, etc. as being some of the bigger elements because when you lose electrons, you're going to lose size in ratio to the electrons lost. For example, let's say you have a pizza box. You have 3 pizza slices. So if we take 3 pizza slices, you're going to feel so empty, right? You're going to be so hungry. Oh my god, I lost 3 slices of pizza and I was starving. However, if you had just 1 pizza slice in the box, and you're like, yeah, I'm hungry, and your roommate or something just takes that pizza and eats it, you won't be as devastated. I guess that's the only metaphor I can use right now, is that if you have 3, you're going down a lot. But if you only have 1 out there, and you lose that 1, it's not as much. So, in general, those electrons that are there are going to be worth more. So let me rephrase that. Boron has 3 electrons in its outer shell, and it's going to lose that 3, and the ones that are remaining, boron's nucleus is going to hold so tightly to those, because they just lost 3 electrons in one go. That's taking a lot of energy to remove those electrons away. On the other hand, with lithium, it only has 1 electron. It's real chill with losing that 1, because it still has those 2 it's used to holding on to. So you can summarize the section by saying there's more shielding when you remove these outer electrons. Or rather, there's suddenly less shielding, but more shielding, and shielding in general is why we have this divergence in the arrows. So, general summary, our bottom left and our bottom right are the biggest for ionic radius. So isotopes, we love isotopes in this household. They're pretty much just elements with a different number of neutrons. And as we remember earlier, neutrons and protons are the only subatomic particles that contribute to the weight of an atom, right? So this pretty much means elements that just have different mass. When we write this out, we would write the nucleon number at the top, so that's protons plus our neutrons, and the proton number at the bottom. So carbon 12 is carbon with a mass of 12, or has 6 protons and 6 neutrons. On the other hand, carbon 14 has 14 nucleons, which 6 are protons, and then we have 8 neutrons. So our mass has changed by an extra 2. And of course, you can probably see here, it's just the element name, dash, and the nucleon number. So isotope properties are really not too hard to memorize overall. Chemically, they have the same chemical reactions, or rather quite similar chemical reactions, because they have the same protons and electrons in there. And electrons are mainly the ones that take place in different chemical reactions. Think of bonding, where we have covalent bonds that share electrons with each other, and we have ionic that steal electrons. And when we have those reactions occur, that's how we get maybe explosions, that's how we get heat increase, etc. So chemically, there is nothing significantly different. However, physically, that is where we see our change, because physically is when we talk about mass, we talk about density. So if the only different part about isotopes is that they have a different weight, that means they're going to have different physical properties overall. This isn't going to affect us very much, I would say, but it'll matter if you have calculations based on isotopes instead of just a standard element. So that is all for that section. So section 3 is about electrons, energy shells, and atomic orbitals. So definitions all around. Some people love them, some people hate them. I'm not too fond of them, but here I have ones that just organize the biggest to smallest you can get. So a shell is just a path of electrons, that's it, just a shell. But the principal quantum number is the number of energy levels or quantum shells. So pretty much this is just a number we would assign to the shell. So we'd have n equals 1 that goes up to 2 electrons. This would be for cases such as hydrogen and helium. They have those 1, 2 electrons. Those 2 electrons, helium is satisfied. But when we go out and expand a little more, we have n equals 2, where we can hold up to 8 electrons. And then n equals 3, 18, n equals 4, 32, and so on and so forth. Generally, I think the max you'll have to write down is 4, but I can't really promise that. You just know that these numbers are increasing, and with each increasing number, you get more atoms and you're getting further away from the nucleus. However, subshells are these regions specifically in the shells where electrons exist in defined areas associated with particular amounts of energy. So I want you to imagine that a shell is like a mall, and there's certain sections or subshells within this mall that have different kinds of value, you could say. For example, we have the food court. It's pretty cheap area in general. We have some stores that are like the average level. We can say the food court is S level, where, alright, it's pretty decent, not too expensive. We have P level, where it might be some general stores, retail stores, etc. Maybe get to $20, $30 for an item in there. Then we have the D block, where that's going to be maybe some of your more luxury stores, maybe some jewelry, perfume maybe. It just associates with specific electrons and specific amounts of energy. And certain blocks are going to have higher amounts of energy. And then we have orbitals, which are just regions of space outside the nucleus that can be occupied by a maximum of 2 electrons. So in our S block we have 1, in P we have 3, D we have 5, F we have 7. You don't need to worry about F block too much. We don't talk about it a lot in the AS level. You have to be aware that it exists in general. Because if we look at this next image, okay, this is one I wanted, that F block is at lanthanides in that section down there, so we don't really have to focus on it for this time being. We just need to focus on going on the upper area. But we do have to talk about what the s orbital and the p orbital look like. The s orbital is just a circle. It's simple as can be, just a circle. However, p block has 3 different ways you can write it. All of these ways are equally correct. However, if an ACE exam gives you 2 or 3 marks on this, you have to write more than one definitely if you want those full marks. We have the one that goes up and down, that's just like an 8. We have the one that goes sort of diagonal, and it's just like a tilted infinity. And we have the one that goes left and right, which is infinity. It's the same symbol, just rotated a few times. And we don't have to focus on D block for drawings wise, so don't worry about it right now. Though I do want to add, a way you can memorize that there's 3 different ways to write the p orbital is that p rhymes with 3. That's sort of what I use. S is a simple circle, and p has 3 ways to write. I don't know how you remember the infinity part. Maybe the p has a loop, so you remember the loop like that. I don't know. It's really not too complex. It's just little drawings, so don't worry too much about it. Alright, now on to electron configuration. How we write electron configuration is by having a principal quantum number, the subshell we are in, and as an exponent, we would have the electron number in orbitals. So, for example, when we look back at this, if we want to look at hydrogen in the top left, that would be 1s1, right? It's pretty simple. Then we move on to helium, it would be 1s2, because we move from 1 electron to 2 electrons. Then lithium would be 2s, well, it would be 1s2 to s1. We sort of build on these shells. So we acknowledge what's closest to nucleus, and then we expand out from there. So there's 2 ways you can write this full configuration is often what ACE wants more. If we want to look at calcium, it would be 1s2, so that's our hydrogen helium, 2s2, which would be lithium, then beryllium, then 2p6, so we're moving from our S block into our P block, so our light blue to the green. And we're covering all 6 of those elements. We still have not reached calcium. We're not going to stop until we reach calcium. So we have 2p6 because we have 6 elements we're covering. Then we go back down to 3s2. Then we go on to 3p6, then 4s2. That's when we reach calcium, so that's when we stop. However, there is another way to write this, a shorthand configuration, or the noble gas configuration, some call it. Pretty much you grab the closest noble gas to whatever you're trying to reach. For this case, it was argon. And then we would add argon 4s2. So pretty much you're summarizing the 1s2 to 3p6 through that brackets argon. But if it does not ask for shorthand configuration or noble gas configuration, you have to write full configuration. You can't just use the shortcut because you want to. It's only if they specifically ask for it. However, we do have some important things to note. So first, I think I'll go over is how chromium and copper are written differently. So chromium is typically 3d4 than 4s2. However, when we write it, we have to write 3d5 4s1. So I know we talked about earlier how for shells, they either want nothing in there or all of it in there. However, for subshells, they want it not full, half full, or completely full. So for the S block can fit a max of 2 electrons. The D block can fit a max of 10 electrons. So we have chromium that it just really wants another electron. It just really wants one. It's at 4. It's almost halfway. And 4s2 is like sort of a pushover. And sort of 4s2 is like, okay, fine, I'll give you it. So we go from 3d4 to 4s2 into 3d5 4s1, as now we have half numbers for both of our orbitals, so both of them are very happy. This makes the electron, not the electron, makes the atom more stable overall. And for copper, it's the same principle. We have 3d9, 4s2, 9 is super close to 10, and they go to 4s, they're like, hey, can you please give me an electron? 4s is pretty much a pushover, and now it is 3d10, 4s1. And it also is the same down that group. For example, elements silver and gold are going to have the same rules as copper because they have that similar electron configuration when you go down. Additionally, when you write electron configuration, we do 1s, then 2s, 2p, 3s, 3p, When you get down to 4s, when D block starts, it starts at 3. That's very, very important because when we write out our electron configuration, we have to write the 3D before the 4s. This is because when we remove electrons, we remove them from 4s before removing them from 3D. It sounds really weird, but it's almost like you have, let's say you have x equals 2 and x equals negative 2 as two of your answers to something. We would put x equals brackets, negative 2, comma 2, and brackets. The way you order them from negative positive just to be polite, I would say. And it's sort of like being polite, but it's also the law. So it's almost like, hey, don't murder someone. It's polite not to murder someone, but also you're legally required not to murder someone. So you have to do it in this way. Or maybe a less extreme one is that when emergency vehicles coming by, you have to pull over on the side of the road just to make sure they can get by. It's like just reordering yourself just to make sure everything goes more smoothly. Man, I'm just like really obsessed with like weird metaphors today. I really don't know why. So we also need to talk about how ions change electron configuration. So an ion, as we previously established, is when an atom loses or gains an electron. For example, beryllium is typically 1s2, 2s2. But beryllium with a +2 charge is going to just be 1s2. This is because electrons are negatively charged, so when we remove an electron, it's getting more positive. For example, oh my god, another metaphor. So let's say you have 4 negative friends around you, and you get rid of 2 of those friends. So you're going to be more positive as a person overall because you drop those bad people in your life. And that's sort of, it's a really weird way of thinking about it, but you're more positive because you lost something, right? On the other hand, with a negative ion, if you're gaining more of those bad people in your life, those toxic people, you're going to be sad, you're going to not feel as well. So when we have oxygen normally is 1s2, 2s2, 2p4, but oxygen with a negative 2 charge, we see that 2p4 turning into 2p6, where point is just adding 2 electrons onto it because the charge was negative 2. So the additional electrons would mean we add however much the charge is at the end. The same with beryllium, we just subtracted 2 electrons from whatever we had previously. So now we have the box notation, or the arrows and boxes form, which there's a lot of words on here, but I promise a lot of it is just the steps in how we do this. So ground state is generally the idea that we get the most stable electron configuration of an atom when we fill in what has the lowest amount of energy first. So for example, that is often, well, that is always 1s, and then we go 2s, and we go 2p, etc. It's almost like, another metaphor, it's almost like when you have a notebook and you write in the first pages first and then go on from there, because it's the most stable way of organizing the information that you have in the book. So you can think of these boxes as the pages in the book, and the arrows that you would put in it as the electrons that you're just trying to organize a little bit. So the first step I'd recommend is to write out the electron configuration. For phosphorus, it is what you see there, 1s2, 2s2, blah 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 blah. And I do not think at all you should write shorthand, because you'll never be asked to write a shorthand boxes notation, so it's just going to hurt you if you don't write out all of the electrons because you don't really know what you're going to draw. So from there, you're going to draw boxes that represent the subshells that you need to draw. For 1s, we need to draw one box. The s is a box. Then for 2s, we would have a box like that. It's a bit separate, it's not connected, because when we go to stuff like 2p, we'd have 3 boxes all together. When we think about the orbitals, an s orbital is just a circle. That circle fits 2 electrons. So we just have one box. However, 2p has 3 orbitals. It has 3 ways you can draw the orbital it has. So it's going to have 3 boxes that are put together. So that's why I so showed you that drawing earlier, because it makes this stuff make a lot more sense, where S, it's just one way to draw it, one box. P has 3 ways to draw it, so it's 3 boxes. And technically, orbitals, the pictures I showed earlier, aren't just ways to draw it, it's also the ways they exist in an atom. Because you would have one S and then a few P's in there, essentially. Because when we think about a shell having 8 electrons, well, when we add that up, S would have 2 electrons, P would have 6 electrons, 2 plus 6 is 8. That's how we generally get those kinds of numbers. But anyway, so we have these boxes laid out for us, and I think you should label the boxes just like how they've been labeled here. That way you don't get confused at all. What we're going to do is put in arrows upwards or downwards for each electron, but you have to make sure you do whatever you do consistently. So for example, I always put the arrows upwards first, because if you don't put the arrows consistently, for example, let's say at 3p at the end, you did up, up, down, right? It's going to ignore the idea of electron spin pair repulsion, because when you have electrons all going the same way, think of them as magnets, where they all have, when you put magnets towards each other, they generally repel each other, right? However, if we have these magnets going the same way, they're not going to be angry at each other, they're not going to repel each other, they're just going to go the straight way. So, ground state is that we need to take the least amount of energy possible, and by making all these electrons face the same way, it's following that principle, and you need to follow that principle when you're doing your boxes notation. So just to make it simple, make sure you do your arrows upwards before going downwards, or always have them going downwards before you make them go upwards. So once you fill in a box, for example, 1s, we put one electron going upwards, and now we still have no electron we need to put in that box. So you fill all the boxes once before doubling up, and then you're going to add an electron going in the opposite way of the first electron we put in. So we had an up arrow, now we're going to add a down arrow. This is because the energy caused by spin pair repulsion is going to be less than jumping up a shell. For example, the jumping from 1s to 2s would take a lot more energy than just two electrons being a little angry at each other for a while. Almost imagine you have this neighbor you really don't like. You just hate that neighbor, they're just so annoying. But living next to that neighbor is a lot easier than just moving across the city, for example. It takes less energy to just coexist amongst each other, and that's pretty much what you do for all these boxes. So you do 1s, we do one arrow up, we're at the end of that box, so we do one arrow down. The same with 2s. Then for 2p, we would do arrow up, arrow up, arrow up. We still have more left over. Arrow down, arrow down, arrow down. And you would follow that idea until you finish your electrons. And also, if we have something like 3p5, that would be arrow up, arrow up, arrow up. Then we start doubling up, arrow down, arrow down. We would not fill in that last box, even if it really wants to be filled, because the electron configuration said it should not be filled. Also, the syllabus said you must know energy organization, so pretty much our energy goes from 1s to 2s to 2p to 3s to 3p, and up to 4s, then back down to 3d. So 3d technically has more energy, but if we remove electrons, it would happen through 4s, because it has a higher principal quantum number. Don't worry if you don't entirely understand this. Knowing AICE, it's going to be just 1 or 2 marks on the exam, but of course, if you do understand it, that's wonderful. Just know that 3D has higher energy than 4s, but 4s would have electrons taken away from it first. It's like how we said earlier that 4s is a pushover. So if they see, oh, things are happening in 3D, I'll sacrifice myself. It's almost like that idea where electrons are taken away from the most outer shell to the 4 shell, before the 3 shell, even if D generally has more energy in it. It's almost like when we had that mall example and we had P being like an alright shop and then a D being expensive shop. It's like the P shop being like, yeah, we should support capitalism, and then the D shop being like, yeah, we should support capitalism. I don't know if that entirely relates to chemistry, but it's just, wait, why did I say P? No, it's like the S offering itself, even if it's like a really small little place. Alrighty, time for our last section, ionization energy. So, ionization energy is measured in kilojoules per mole. And the first ionization energy, I'd recommend memorizing this definition because I've seen it come up on past exams before. It is the amount of energy required to remove 1 mole of electrons from 1 mole of gaseous atoms of an element to form 1 mole of gaseous 1 plus ions. I've underlined some things here, but also we want to note that these are gaseous atoms, so ionization energy only applies when it's a gas. And And along with knowing this word definition, you should know the equation down here, where X is like any kind of element, where an element in gas form will turn into an element with 1 plus charge, plus an electron, because if we add these together, 1 plus 1 minus would equal the 0 again, so these charges are still going to balance out. Ionization energy is just the energy required to make this reaction happen, to allow that electron to be removed from the atom. It's almost like how much energy would be required to be an activation energy. I wouldn't say a catalyst because energy itself is not inherently a catalyst, because catalysts only speed up reactions, but it's how much energy you need for this to happen. And later, as we graph out some of this energy, it'll start to make more sense. But then we have second ionization energy, where it's pretty much the same exact reaction, except we go from 1 plus ions to 2 plus ions. So when we have first ionization energy, it goes to 1 plus. Then go to second, it goes to 2 plus. It's the same reaction you see below, but the charges on the elements are going to change. So you aren't going to write that X goes into X2 plus 2 electrons, you're going to write 1 plus into 2 plus. The word in front of ionization energy just tells you what charge the element is going to have in the end, if that helps as a tip. So here's the graph I was talking about earlier. Here are the first ionization energies for successive elements, so elements that are next to each other on the periodic table. For example, the atomic number is at the bottom, so this would go in hydrogen, helium, etc., etc. And the ionization energy in EV. I know we just said the unit is kilojoules per mole. They just put it in electron volts, which we are never going to use that. You don't have to worry about that on your AICE exam. It's just a public resource and I put it in there. But generally, we need to talk about the trends that happen in this. So this is where we see some of our key terms, our 4 key terms I talked about earlier, coming back into place. So from elements 2 to 3, we're seeing a large decrease, and this is because we're jumping in group numbers. We're jumping the period overall, because we're going from the first period to the second period. We're going from helium to lithium, if you can imagine that on a periodic table. So with this, we're having another shell added, so we're having increased distance and increased shielding. That makes that one only valence electron really easy to remove. Now what I mean by this is that extra electron we're having on the outside there is in another shell. It's farther away from the nucleus. So even though we have our nuclear charge technically increased, this increased distance and shielding are going to outweigh that extra charge, because the addition of that extra subshell is very significant when we talk about energy. I'll try to make a metaphor for this. So we're having groups of students study. We have groups of 4, then we have a group of 1. And who is more likely to not be held accountable for their work? The group of 4 is likely to hold each other accountable. Hey, if I'm working, you have to too, while the one person might just go on their phone and scroll through TikTok. So as a sort of summary, that one student or the one electron can be easily removed from the situation. You could sort of say it like that. Then from the atomic number 3 to 4, we see a small increase in ionization energy, meaning it's taking more energy to remove the next electron. This is because we have a full shell that forms. And for this case, it is the S subshell that is being filled. Though we're not seeing a super big jump because we're not jumping in periods, and also there is some spin pair repulsion, so sort of balance that out a little bit. Then from the atomic numbers 4 to 5, we have just a very small decrease. This is because we're jumping to the next subshell from S to P. We have 1 electron by itself. That's going to be a lot easier to remove, though our number 5 electron is still at a higher ionization energy level than the 3 electron, because it is in a higher energy group, you could say. Like the P requires more energy to remove than the S. Then from our 5 to 7, we're seeing just a very general increase, a very linear line right there. That is because we're having spin pair repulsion induced, as we're adding these more electrons in the same P subshell. And then from 7 to 8, we have a small decrease, because at 7, we had a half full orbital. What I mean by that is that we had, it's not 6, so it's 5, 6, 7. A P subshell can hold a max of 6 electrons, half of that's 3. So at 3, it was sort of happy, it was doing good. Then it dropped back down to 4. So if it wanted to remove that 1 electron, it'd be a little easier, because removing that 1 electron would make the atom more stable overall. Then after that we have 8, 9, 10, which is just filling up the rest of that P subshell. Then we have a large decrease, which we can just go back again. The 2 to 3, how we had the large decrease jumping group. The trends repeat on themselves, and you can see that as it progresses. And while we have the graph over here, we can see how it labels the atomic numbers for this. This one does not label them, and on the AICE exam, you will often more than not have one that's unlabeled, and you need to figure out what elements are there. They may tell you the period it's in, so like the row, but you need to figure out the groups. So the best way to do this is look for the very large jumps, as a very large jump equals the group change. So that means it's group 18. So the one that's 1, 2, 3, 4, 5, the fifth dot right there is the group 18 dot. And you can also count backwards from there, or you could see how it goes up like 3 in a row, so you know you're in P, and you're not like going up anymore after that. So that means you're in P block, right? Because essentially the S can only handle the 2 electrons before having to jump into down and then up into 3, down, up into 3, then big down as it goes into the group change. But generally, you want to look for the very large decreases. That's what's going to help you the most. So it was implied earlier, but I'll restate that for ionization energy, it is the biggest in the top right. Towards the right is because there is increased nuclear charge, and it's harder to remove an electron that's attracted to a stronger nucleus. If there's more attraction, then it's gonna not want to leave as easily. You'll need more energy to remove it. And the reason why it is a higher ionization energy in that top right and the bottom is because there's lower distance from the nucleus for those outer electrons, and there's less shielding from those inner electrons. So, for example, helium is going to have very high ionization energy levels. It only has 2 electrons, so it really doesn't want to get rid of those, if that makes sense. Alright, next we have the successive ionization energy of an element. Previously we just talked about the first ionization energy of successive elements, and now we're talking about successive ionization energy of an element. So you can see the underlined bits are what is being continuous. For the other one, this one, so we would have changes in groups, we would have all this kind of stuff. We're going to have a lot of different elements involved, and it's only the first ionization energy, so we're only removing 1 electron from each of these elements. While on the other hand, for this, we're removing 1, 2, 3, 4, 5, so on and so forth, of 1 element, and for this case it's aluminum. I'd say the main way you can tell the difference between these two is that the ones for 1 element are constantly going up. You will never see them go significantly down like they do in the previous one. And this is because as you're constantly removing electrons from 1 element, it is constantly going to take more energy to remove other elements. We might see a very small, no, never mind, it's not even a decrease. I was going to say 2 to 3, but no, that still looks like it's an increase. So yeah, these are never going to significantly decrease like the other one did. Though we should still talk about general trends with this. From the electrons removed from 1 to 3, we see it's generally consistent and low. They have the most distance and shielding. They're the most outer electrons are valence electrons. Then the 3 to 4 we see decent jump. This indicates a changing period. We're going from our S into our P. So we're not going S into P as in we're increasing, but S to P as we're decreasing. So we're jumping a period like upwards, not as an up as number wise, but like if you look at the periodic table, you would go up, if that makes sense. Then from 4 to 11, it's consistent and it's at like a medium energy level, I'd say. They have less distance and shielding from the nucleus as before. Oh, well these electrons had the same shielding, but the outer previous electrons had more shielding, that makes sense. Like, electrons 1 to 3 had another ring between them and the nucleus, but these ones are the ring that was protecting them previously, so now they are vulnerable, and that's why it takes more energy to remove them. But because there are no jumps in the distance or shielding, so no like very significant changes happening, it's just a constant increase. It's a very linear line, you could say. And then from 11 to 12, we have a decent jump once more. That is a change in period, and from so on and so forth, it just repeats. So while they may be able to give you a graph like we just saw here, they can also give you a table. So what this table means is you still look for jumps. The jumps idea is never going to change for this section of the chapter. And there's 2 things you could do. You could graph it out, I do not think you should ever graph this out, but if that's how you get the mark, that's how you get the mark. But I would say you should look for the biggest multiple. So, for example, we're going from the first ionization energy to the second. It is 577 to 1800. I just said in my head, okay, that's about 3, and I moved on. Second to third, that's less than 2, so on and so forth. When you do this for the whole list, you don't have to do it for the whole list, but I did just to show you how this works. We see that from 3 to 4, we have 5 as a multiple. So when we're going from 2,700 to 11,000, and also when we go to 11 to 7, which if I look, it is 42,000 to 200,000. So pretty very clear jumps compared to all the other ones in my list being less than 2. So when we do this, we would look at the first number between the change. So between 3 and 4, we would look at the 3. If we look between 11 and 12, we would look at the 11. So once we establish the number we're looking at, it's just very simple. The element is in group 3, and that's commonly what they ask you, what a group is it in? And maybe they'll even tell you the period, that we can say, oh yeah, if it's in this period and it's in group 3, that means it's X element. But also, when we look at further, since I'm giving you like an entire table ACE, I'd say they usually give you like maybe 5 or 6 rows. They don't give you like a big table like this. But when we look further, we see that huge jump from my brain's empty, so from 11 to 12. So that is representing our jump from 2s to 1s. So electrons 12 and 13 are our last electrons. That's why it's such a big amount of energy to remove them. And that conclusion is supported by it being aluminum, again, because aluminum only has 13 electrons, I believe, so it is going to really want those last ones. It really doesn't want to be a completely positive ion. That's going to make it very unstable. And I want to say thank you. Thank you for staying with me. Thank you for watching this video. I know chemistry can be hard, but I really appreciate you getting through this. I hope you have a good one. Bye!